Okay, hello class. Here we are at the third video of the week. This is going to be case study 2A notes part 3 titled confidence intervals. Okay, so we left off last time talking about, well, how do we get that t value that we're going to then go and use in our confidence interval? All right, so confidence intervals for mu in case study 2A. So just a reminder, our parameter mu is the average pulse wave velocity for kids with HGPS. The first example, the first practice, I guess we should say, we're going to get with confidence intervals is with case study 2A. And so part of interpreting a confidence interval is knowing what the parameter is. So we're going to use these words when we interpret our first confidence interval. All right, the purpose of a confidence interval for mu is to build a range of guesses for mu. Remember, to build a range of guesses for your parameter is the definition of what a confidence interval, gives a researcher. So a confidence interval formula for mu when we have a t-distribution is as follows. X bar plus or minus t subscript degrees of freedom, comma, alpha over 2 times s over the square root of n. Okay, I've said this before in the past. Don't let subscripts, worry you at all. Subscripts just tell us something about that t-distribution. So all of this is what we would then replace with that number if we were doing a 90% confidence interval for mu. Okay, so to be a little more thorough, the subscripts we would have for this guy would be alpha over 2, so that 0.05, okay, comma, the degrees of freedom from above of 17. All right, so I'll go ahead, get that out of your way, make sure that you have that formula. Okay, and now we're going to go straight. We've done confidence intervals before. We've shown you how to get those values off your chart. Hopefully you referred to the T practice that was posted on D2L. Okay, when building a confidence interval, a reminder, make sure you state the formula, show your values plugged in, calculate the confidence interval, and write a complete sentence explaining that confidence interval. Okay, you can round values to 2 decimal places. All right, so and to make us note, that's you can round final values to 2 decimal places. Any number you get off the chart, you want to be sure you use that entire value. All right, so build a 90% confidence interval for the average PWV values for HGPS kids based on the data from case study 2A. Okay, in case study 2A, it gave you a list of data. So you can either use your calculator or use StatCrunch to calculate X bar and S. Okay, so that's literally just typing in, each data point. The data started with 7.2, 7.9, 8.3, and so on and so on. So you type that number into StatCrunch and it can give you the summary statistics. X bar equals 12.44, S equals 3.64, and our sample size is 18. Okay. Whoop. So here we start always with stating what our formula is. Okay. I'm going to zoom in a little bit and draw a picture of my confidence interval. All right. So we want a 90% confidence interval. So we put 90 in the center, subtract, and these t values are what we're after. So we do 1 minus 0.90 divide by 2, and that leaves us with 0.05. That's what goes in each tail. Okay, so now we're off to the t-table to figure out, well, what exactly is this question mark value? Okay, so I'm going to use my degrees of freedom. So looking over here, if my sample size is 18, what does that make my degrees of freedom? Yes, you're right, n minus 1 is 17. Okay, so I'm going to be utilizing that number of 17 degrees of freedom and 0.05. So if we come here, let's start fresh. All right, so we need to come down to degrees of freedom 17. There we go. And we're looking at the area of 0.025. So come down. Oops. Nope, not looking at the area of 0.025. What area are we looking at? 0.05. All right. So again, going back and forth, we're using, let me make this a little clearer. We're using degrees of freedom 17, an area of 0.05. So here we are, degrees of freedom 17, area of 0.05. We go down 1.7396, which if you remember from the last video, that's kind of the same, similar problem we left off at, okay? So we've got 1.7396. All right, so the next step is to just show everything, all your values plugged into your formula. So your X bar is 12.44. The value you're gonna plug in for T is 1.7396. Your value for S is 3.64 divided by the square root of your sample size. Okay, if you want to get some practice calculating this confidence interval on your own, go ahead, pause this right now. Otherwise, I'm going to keep on going, okay? You know how I like to solve confidence intervals. I like to solve everything to the left, to the right of the plus minus first. So evaluating what I have in that purple box will give me 1.49, okay? So now at this point, this is where I have rounded. Let me get different colors to kind of note this. This is the point where you can round to 2 decimal places, okay? So then you take 12.44, you subtract 1.49 from it, and then you take 12.44, add 1.49 to it, and you should get 10.95 to 13.93. And that is our confidence interval. Now, the last thing we need to do is interpret our confidence interval. And the way we interpret our confidence interval is we say we are blank % confident that our parameter is between blank and blank, okay? So keep in mind, I defined our parameter up here, mu, the average PWV value for all kids with HGPS. So we are 90% confident that our parameter, the average PWV value for all children with HGPS, is between 10.95 meters per second and 13.93 meters per second. I definitely think it's important to go ahead and put units here. Anytime you're writing a concluding sentence, include anything that could be useful to whoever you are doing this research for. Okay, so we're using an old idea that we already should be a little bit comfortable with, confidence intervals, and we're just incorporating this new idea of, well, how do I find that confidence interval, that table value on my T-chart? Okay, let's look at a new question. All right, so this is a project question from a student from a previous semester. All this data that you see and these pictures are examples of how you would see output from StatCrunch, okay? So hopefully when you're doing your descriptive statistics homework, you got a little practice using StatCrunch. It can be very helpful. It can give us a lot of information very quickly. Okay, so this student's project question was, does the average length of forest tent caterpillar moth larvae in the Nacogdoches area differ from the national average of 50 millimeters? Okay, she collected a sample of 32 forest tent caterpillar moth larvae and had the summary statistics, histogram, and box plot that you see below. After the student ran her hypothesis test, she calculated a confidence interval to build a range of guesses for the average length of forest tent caterpillar moth larvae in the Nacogdoches area. All right, now I want you to build a 95% confidence interval for the average length of forest tent caterpillar moth larvae in the Nacogdoches area. All right, so we should have a pretty good idea that we are going to be using the t-distribution, but this is a good time to bring up the requirements, okay? The requirements are that we use S to estimate sigma, which we have. The standard deviation is S. So we have S to estimate sigma. The other thing we need is an approximately normal distribution. Now, looking at this histogram, do you believe we have an approximately normal distribution? Okay, and the way you can also answer this question is, can you draw a symmetric bell-shaped curve over it? And really, anytime you see a histogram, I'm always going to encourage you, go ahead, trace your line, draw a general shape over the top. And yes, that does look like an approximately normal distribution. Okay, so the other value you're going to need to know from this summary statistics is X bar. Okay, so we need X bar and we need S in order to plug into this formula. Okay, so here I am, X bar plus or minus my table value times S divided by the square root of N. Okay, so we have X bar, we have S, we have N, and now we just need our table value. Okay, so I'm gonna draw my little picture here off to the side. Okay, and we want a 95% confidence interval. Okay, so what area or what value is gonna go in this shaded area? It's gonna be 0.025, all right? Reminder of how we got that, 1 minus 0.95 divided by 2. Okay, so now we need to take our upper tail value and our degrees of freedom to the chart. If our sample size is n, what is our degrees of freedom going to be? Yes, it is going to be 31. So again, let's start fresh here. Okay, let's go to degrees of freedom 31. All right, and zoom out a little. We were looking at the area of 0.025. So 0.025 all the way down, we see 2.0395. So 2.0395. That is going to be what our question mark is. Okay, so the next thing I need to do is show all your values plugged in. Again, any value from any chart, you want to just go ahead and use all the decimal places. Wait until the last step when you're adding and subtracting to round. Okay, so take a moment, pause. I want you to try this confidence interval on your own. Okay, so you should get 51.08 to 59.74. Okay, and so what does that mean? It means we are 95% confident that the average length of forest tent caterpillar moth larvae in the Nacogdoches area is between 51.08 millimeters and 59.74 millimeters. Okay, that was another example of our practice with confidence intervals. Okay, so now what we did in the last video, or the first video, is we realized, hey, we need a new test statistic, and we looked at what our new test statistic would be. Then in the second video, we looked at calculating, sorry guys. We looked at the table and we got p-values. So we're not actually calculating p-values. We're estimating our p-value based off the table. And then we also looked at now confidence intervals, okay? So we're now in a place to go ahead and complete case study 2A, all right? So we started last time, we did the first 5 ingredients, we set up the null and alternative hypothesis, and we talked about type 1 and type 2 errors. Okay, so now give the test statistic, box the value of that test statistic. Okay, so what are those requirements? Okay, I'm going to keep emphasizing them. The requirements are important. Okay, we need an approximately normal distribution, which we have if you look at the shape of our histogram in case study 2A. Okay, and sigma is unknown and estimated with S. Okay, so jumping back a little bit, that means the formula that we're going to use is X bar, T equals X bar minus mu over S divided by the square root of N. Okay, go ahead, write that down, and I'm going to scroll up to where we have our info for case study 2A. So we had our info right up here. All right, So what we're going to plug in for X bar is our 12.44. What we're going to plug in for S is 3.64, and N, our sample size, is 18. Okay. I also want to just make a note off to the side. Something that can always be helpful to us is to remember what our alternative hypothesis is. Mu is larger than 6.6. Okay, so go ahead, plug all those numbers in to that T formula and type it in your calculator and see what you get as your value for T. Okay, and when you plug those into your calculator, I want you to note that you want to do parentheses around the top and parentheses around the bottom in order to get the correct value. All right, and you should hopefully get T equals 6.81. All right, so that is our test statistic box, the value of the test statistic. Okay, the null distribution or the sampling distribution. What is the distribution of our test statistic? Okay, T follows a T distribution with 17 degrees of freedom. All right, so I kind of wanted to make a note again here that T17 is referring to the curve. Okay, T17 is the particular distribution. That's the line of degrees of freedom you're going to go to on your chart. This first T is referring to the actual test statistic. How is our test statistic distributed? Okay, but T squiggle, T17, okay, how you say that is that T follows a student's T distribution with 17 degrees of freedom, okay? Go back to the notes prior to this. I talked about how you say it versus how you write it, okay? So here is how you would write it. All right, now I need to calculate the p-value. All right. Oops, I was supposed to leave myself a little bit of space and I didn't. Okay, calculate the p-value. So you have 6.81. All right, so I want to zoom in right here and draw my picture. Okay, again, this is going to be T17. This number line continues indefinitely. So I'm at here at about 6.81, okay? Now, what we need to remember about our p-value is we always have to start with our probability statement, okay? And where does our probability statement come from? No other than, of course, our definition of p-value. All right, so the p-value is the probability of observing the value of our test statistic, or more extreme, if HO is true. So the probability that T is going to be greater than or equal to 6.81. Okay, I got that greater than from HA. I got 6.81 from the calculated test statistic. And then, so my picture is that I'm going to want to shade everything above 6.81. All right, so I'm going to go to my Z table. With this problem, we have a sample size of 18. I'm going to zoom in. I have a sample size of 18, and I'm looking for the t-value of 6.81. So I'm going to start here at 18. Oh, 18 is our sample size, so what's our degrees of freedom? Yeah, degrees of freedom, 17. So I'm here at 17, and I'm going to scan across, and I'm looking for the number 6.81. And I get all the way to the end and notice, 6.81 isn't on there, okay? The last value we have is 3.6458. All right, so 6.81 is definitely further off this chart, somewhere down there, okay? Now I want you to look at the top. Look at these areas. They start at 0.2, 0.15, 0.1, 0.1, slowly getting lower and lower, okay? So what do I know about 6.81? if I were to go to the top and pick off this area, okay, this number right here would be smaller than 0.001. So that makes our answer that our p-value, that was my p-value statement, is smaller than 0.001. Okay, if you would like a little bit more of an explanation for that, notice, let me erase some of this. The last value here is 3.6458. So 3.6458 is associated with 0.001. Okay, let's see if I can remember all those numbers. 3.6458. So if I were to draw my curve, 3.6458. The area above 3.6458 is 0.001. So if I were to, maybe shade that in a slightly different color, that incorporates all of the area above 3.6458, including the area above 6.81. Okay, so if we know that everything shaded in pink is 0.001, but what we want is shaded in blue and is a little bit smaller, then we know that this blue area must be smaller than the pink area, which is the last number it gives us on our chart. So even if numbers fall off the chart in either direction, well, we can just either say, well, let's look at the chart. If it falls off the chart in this direction, well, then that means our probability is smaller than 0.001. If our number falls off the chart in this direction over here, then that means our number must be, I should say our probability must be bigger than 0.2. Okay, again, there's a little more practice that maybe hopefully you got when you looked at that T distribution practice I posted on D2L. Okay, so calculating that test statistic, writing that null distribution, calculating the p-value, that was kind of new stuff, but now it's come to making a decision and writing a conclusion. This is going to be the same as it always has. So is our p-value low? Yes, our p-value is low. It's smaller than 0.001, so our p-value is lower than any reasonable significance level. Okay, so that makes our decision reject HO and accept HA. The conclusion, we have evidence that the average PWV value for all children with HGPS is greater than 6.6 meters per second. Okay, that is, we do have evidence that the average pulse wave velocity value for all children with HGPS is indeed abnormal. Okay, so the next thing I have here is build a 95% confidence interval. I'm going to leave this here for y'all to practice. You can look back up at the previous confidence interval problems that we had just started. And I think that is going to be all for this note set.